Derek, Drew Pritchard, sorry, Michael Kimball, Jacob Miller, Daniel Ramirez, not here. Is there something going on today? Memphis, not here. Riley, you're here. Alex, here. Brandon, you know what you do. Samantha, do you want his too?
Yeah.
And I guess that's it. Okay. I think I put the quiz solutions up. Are they up?
I have not worked on one night.
Is there something going on? Why everybody's missing?
I don't think so.
I know the guy behind me is doing some sort of test, but I don't know about the rest.
Yes.
Yeah, he's very good about it,
You need study for it?
like an online test.
Oh. Let me just make sure it's on, that this stuff's up. And,
I don't see.
it will be in 1 second if it's not, that's on me. I grade these things on Friday, right after, I usually grade right after class. And,
I don't think quiz 5 is on here either.
give me 1 second, they should, unless it didn't sync, which is entirely possible.
Refreshing.
I think you might be right, actually. That's quiz 6.
Drew, you want to hear something super annoying in the place I just moved into?
What's that?
Just someplace I moved into. It's not related to the class. The coax cable, there's like a million sticking out of the floor. All electrical, it's like a 1920s house. You can tell they came into the basement and did everything through that.
Has it not been too big?
I had hooked up all the stuff and I can't get a signal. And I'm like, well, probably because there's 50 splitters down in the basement and he's got a personal padlock. The owner has a personal padlock on the basement.
You said from the 1920s?
Yeah, it's like
Is
a
that
19
house even grounded?
Mm-hmm. And so, like, man, like, I've got an appointment for them to like come check the internet because I need the signal check. I don't have one, and I'm just gonna cut the lock off. I'm renting the place. I'm paying for it. He told me I need to be able to change air filters, so I need to get down to where because the air AC's in the floor too.
Mm-hmm.
So it's like, okay, well, I need to do the job. So
Can you see if that stuff's synced? I want to make sure everybody has this.
Quiz 6 is on here. Yeah.
All right, so here's what I proposed to do. Hopefully some more people show. We only got 6 people. I'm gonna put up a PowerPoint briefly and just go through And then we'll work the problems. Did you look at the problems? Everybody? Nobody. All right, we work at the problems in chapter 6, section 2, and then 3. But I want to go through these, and I'm going to try to make some points. Now, this is kind of, it's going to get a little more confusing. And I want to make sure that you guys at least appreciate this for what it is. Let's see. Screen. I should ask this. Does anybody have any questions about anything? I normally ask that right off the bat. If you didn't do the problems, I'll go. The first set is not bad, but by the time you get in the third set, it gets confusing, you know? Or the section 3 problems, you know what I mean? I say this because when I've taught this class before, I found that there are certain sections where people just have trouble with it. I mean, they just do. And you can, I can't say the reason for sure, but to me, a lot of times the stuff is more confusing. So I'm going to go through this and try to make some points about what's really important. So this is chapter 6, and it's Denny's notes, but he does a great job of identifying the real problems. First, when you do an autocorrelation function, one of the questions everybody should have in their mind is, why do we care? That's the number one thing. Well, at least applied to my work with radar stuff, if you go ahead and you have a data, you collect data, you transmit a signal, you collect data, you got a whole bunch of data. Now, there's a lot of things you can do. One of the things you have with that data is a lot of noise. And because you have a data record, you can process, you can do whatever you want with it. And the autocorrelation function will allow you to do something where now you get a relationship between any part in the reflected signal that you record and any other part. Then when you actually, and we'll see this later, you take the actual spectral density function of it, the Fourier transform, now you can see a lot more information. You can see where jamming signals are and all that stuff. The autocorrelation does not tell you anything about the distance to the target or anything in my world. But when we do what's called a cross-correlation function, then you can get the exact distance and everything. I'll try to show you this later. So to me, this is valuable. And there's a lot more information that I can tell you about. But really, when you get a data recording of a signal, if it's encrypted, at least, now you can't decrypt it, right? But if you do something, and this is all basic information here that you'll start learning about in communications. If you do the autocorrelation function, and you see peaks, all these peaks, that means that those signals, there's something in there that's related, the past part to the future part, and the only way that happens is really somebody intentionally designed that. Have you all heard of something called SETI, the Search for Extraterrestrial Life or Intelligence? All right. Well, when they listen out there, they record all these, basically, they got nothing better to do kind of thing. But long ago, they recorded this thing, and when they looked at the spectral content, and I'm not sure if they did autocorrelation or not, but they found that there was a relationship, a very strong relationship between two parts of their signal that they recorded. And the only way that can be, it can't be wide, it can't be anything naturally occurring that we know of at least. There had to be something that was man-made. Well, it's likely a reflected signal that they just happened to capture. They weren't unaware of it, but nobody, I can't say that with certainty. Okay, back to this thing. So autocorrelation function is valuable to me because I can get a lot of information using it. And you'll see a cross-correlation function that has to do with two different signals, not one signal, will give you an enormous amount of information. So basically, I think you all follow me on this, that what we're really doing when we do an autocorrelation, we're taking the expected value of two parts of a signal. You don't have to write this down, but just listen to me. When you talk about signals in time, I mentioned this already, you can take the time average of any kind of a signal, and you can get an average value. Or, if we have the probability density function, then we can take the probability density function, we can take like if we want the average value, x times f of x integrated over all the regime that it exists in, and you can get the value. Now, if the time domain average is the same as the space, or as the probability density, it's called the ensemble average, then it's called wide sense stationary and ergodic, and I'm not going to split the difference on those two. And everything we're going to be talking about is going to be wide sense stationary. If it's not wide sense stationary, I mentioned, do you remember what I said was a good example of that? Anybody? From Friday? Todd? No? What's one thing that you know changes every 24 hours? The Earth
The
rotates,
sun.
and the ion density and the ionosphere will go from a very high amount during the day to a very low amount at night. That's the thing. So when you talk about the probability density functions for the ion densities, they are time varying. So an ensemble average of the density doesn't necessarily mean it will be equal to, in other words, if you take the probability density function, they do have these, believe it or not, for the daytime atmosphere right above Auburn, Alabama, let's say 100,000 kilometers, and I should say, yeah, 100 kilometers. And you go ahead and then you take the average velocities, let's do it this way, not density, average velocity or the mean energy at this time of day, it will be different at 12 hours from now. It will be a lot different. So it will not be equal to the time average, that's my whole point. That's an example of something that is not ergodic or wide sense stationary. But almost everything that you will be involved in, that I can think of at least, you can assume that. Okay, enough said. Back to this thing. So you look at that signal, this kind of stuff, instead of, they have these data record strips of the electric field intensity, all this stuff. When I look at this, I don't see anything as far as the relationship of one part of the signal to the other. So if I go ahead and I do an autocorrelation of this, one thing I see is what looks like just noise, and then I get a peak right at zero. You always get a peak right at zero if it's a legitimate operation and it's a legitimate autocorrelation function. Always, it'll be a peak. You might have multiple peaks if there's a time harmonic period, but you'll never get, I mean, at zero, it's always at least the peak value. There may be other peaks, or I should say other maximums that have the same value, but that will be the maximum possible value. So obviously that's a faster varying signal than this one, and you can see one thing that happens. The peak at the center starts broadening. That'll be an important point later in the lecture. The slower the variation of the signal here, or you can see it's got a high frequency component. The actual wider the width of that base level pulse right there, or basically the lag time here is going to start spreading. Here's an example. This is the one you gave me the answer to. I think you remember this. If you have x of t is this, and it's between 0 and 1, you can get this value and 0 elsewhere. Well, one thing you know is, anytime the time lag is greater than 1, the expected value is 0. You follow me on that? So if you look at this, this is pretty straightforward. This is a square, right? It just has a value of a between 0 and 1 and 0 else. When you do the expected value of this, well, it's the expected value of the density function, which would be the ensemble average. Do y'all follow? I mean, this is going to be expected value. This is the autocorrelation of this function. We could write the math for this and do it, but it's going to be the expected value of a squared. If it's uniformly spread from -12 to 12, that's the variance, if you think about it, because the average value of that signal is 0, right? From -12 to 12, and that's 48. Right here, in between when T1 and T2 are between 0 and 1. Really, if tau, and I'm just cutting to the chase on this, tau would be the difference in the first position of x measured and the second position in time. And 0 elsewhere, so it's a real trivial example. Here's one of the problems people have. Whenever they say, see, this has got a probability of all sorts of values, and the autocorrelation of these two signals, you can actually get you basically have to get the expected value of a squared here, which is going to be the variance of A. And it's laid out right in front of you, but people fumble stuff like this on quizzes. And in general, this is what I mentioned earlier, that if it's wide sense stationary, and then this is going to be the case. That the time, if you take a look at the expected value in time, it's going to be the expected value, space, or with a density function called the ensemble. That's it. Have you had this in any other class, by the way? Autocorrelation or correlation? Nothing? Didn't you?
We have correlation, we haven't talked about autocorrelation.
Okay, well, correlation in general is a relationship between one signal and another. Autocorrelation is the signal with itself, with its time skew. And then cross correlation is probably the one you're used to. That's the signal with another signal. And there's correlation coefficient. This is stuff we did earlier. Okay, back to this. This is the example I put on the board Friday. You all remember that? All right, I want to tell you one thing. See how he gives you the autocorrelation function of X? This one's worth going over. I may do this on the board just because it's an important one. All right, X of t is something that they know the autocorrelation function of right there. Now, how they know it doesn't matter. They just give it to you. If they know that, and then they want the autocorrelation function of a new variable z. Now you can see this tau 1 there is a fixed constant value. So whatever x of t is, you're going to have x of t plus tau 1 there. And a legitimate question is, well, how do you know what x of t is versus all time? This assumes, at least a good way to think about it, is they have a data record. This kind of stuff you can't do real time, like real-time fast processing. It always requires some data record. It can be an abbreviated data record. And here I have a question for you. Have you used oscilloscopes and get the fast Fourier transform signals? In what class?
Radio.
All right. Now the fast Fourier transform only works when you have a data record. You have to get a certain amount of data to do a fast Fourier transform. It's not instantaneous, real time. There's always going to be some time delay between what they're showing and the current signal. But nevertheless, a fast Fourier transform is a data record. Here, the only way you can do this particular thing is you have to have access to a data record of x of t to do this. There's no way you can do it like in real time on the fly kind of deal. Okay, so you have this. Now, obviously, if you got x of t and we want, or I mean z of t, and we want the autocorrelation function of that, more or less r sub z, then you're going to have this value here, and we're going to multiply it by this z of t plus tau, so it would be x of t plus tau, x of t plus tau 1 plus tau, and then you're multiplying them out. That's what he's showing here. He's just taking the formal definition here, and he's applying this definition of z of t, and he gets these terms, 4 terms, and he does the multiplication, and there's some points I'm going to make here that you have to notice, or else you'll mess up. Once you do the multiplication, does everybody see this times this? I should say first times, the first one's x of t times x of t plus tau gives you this term. Y'all follow me on that? Can y'all see this, Clive? Now, real quick question. What is that I'm circling? Can you tell? Isn't that the very definition given here? Can you all see that? This first term right here is defined as that. So could replace that by simply e to the minus tau squared. Follow me, class? Can you see it, Todd? Oh, pardon me. All right. Now, the next term, so it's first inside. So if you take a look at this, I multiply this times this. This is an important point. Matter of fact, because this is kind of important, I did this on the board, but I'm gonna use that part of the board and just do this. And I want, because there's some points here that I'm gonna make, and I didn't really make it yet, but when you take a look at, oh, I did make it on front.
Yeah, we got all the way, we didn't do the very last bit with like the 2, you pointed out that it was 2e to the minus tau.
We're gonna do this whole, the reason I'm doing this whole thing is because this one has a lot of, there are behaviors here, if you understand it and see it, it will be extremely helpful going through the next part. Now, one thing, you see how really, the only thing that matters here is the time difference between the first x of t and the second x of t plus tau. So you can replace that tau, and you'll notice Rx of tau right here only has to do with the difference. Do you all follow me on this, class? The tau. Now going back to this thing, and I'll put it up here, the answer's there, but I think it's worthy to mention right here. First, he's going to say, I hope this works, and it doesn't. We're going to do a little trash today. If anything doesn't work, it's going to get tossed. I'll leave it here. So I'm going to have x of t, and we know the autocorrelation function of that is simply equal to e to the minus tau squared. Then we have some z of t, and that's equal to x of t plus x of t, and he calls it tau 1. I prefer a different symbol, but that's what he uses. Everybody's got that, right? Now, the formal definition of the autocorrelation function of z, r of z of tau, is equal to the expected value of, and here it would be z of t times z of t plus tau. Just by definition, I don't think anybody's going to argue with that, right? So then, if I go ahead and replace z of t with its definition right here, now I get r z of tau equal to the expected value of, and here's 4 terms, and it's going to be x of t plus x of t plus tau 1, and it's going to be times x of t plus tau plus x of t plus tau 1 plus tau. And here you got 4 terms, and I think, can you all follow me on this, class? Just to put it down, put it straight. Now, I'm going to go ahead and just break these things out. So the first term is, this, so it's really the expected value of x of t times x of t plus tau. You might as well just put a bar over that, because that is the expected, the average value expected. And then the second one, y'all follow me, first, then the inside. So it's going to be plus x of t plus tau 1 times x of t plus tau with a bar. There's going to be 4 terms. Finally, the next term is going to be, that's the inside, outside is going to be plus x of, and it's going to be t times x of t plus tau 1 plus tau, and that's going to have a bar. And finally, the last term is plus x of t plus tau 1 times x of t plus tau 1 plus tau. And those are the 4 terms. I hope you can see them. Try not to push. I want to leave that up there. Y'all with me on this? I mentioned this already, but if you look at this, this is the expected value of these two. And that is the very definition of the autocorrelation. So when I, of x of t, so I'll put this up here. So my r z of tau here would be equal to can you all see it over there? Okay. What I'm really saying is, when I look at this, that's the definition of the autocorrelation. So here, when I look at this, this is just equal to that thing, right? So that's equal to simply e to the minus tau squared. Then, the next term, that's this one. If you look at this, just take either of these terms and subtract it from another. So I get, if I subtract, take this term, t plus tau minus this, I get tau minus tau 1. Can you all see this, class? You're subtracting the arguments, these two arguments. It doesn't matter, because the autocorrelation is symmetric, don't worry about the negative sign. Y'all with me? Can you all see this right here, what I'm doing? This has t plus tau 1, right? This has t plus tau. So take this argument, t plus tau, and subtract this argument from it. The t's go, right? And you're left with tau minus tau 1. Can you all see? So that's going to be the autocorrelation here of tau minus tau 1. That means this becomes tau minus tau 1. So it's going to be e to the minus, you can put an absolute value here if you want, tau minus tau 1. Can you all follow me? Yes, sir.
How does the algebra work out where you subtract?
All right, look, if you, let me come over here. If you take a look at what I have there, I want the definition of r of tau is equal to the expected value of call it of x. Expected value of x of t, right, times x of t plus tau, right? All right, now what am I really doing to get that? Well, I can take a look at this, and I'm really saying if I have this argument, the only thing I'm really looking for is the time difference, right? That is tau. Can you all see? Right. So what is the time difference? I usually use the one with tau in it, so I can take t plus tau, and I subtract from this argument, from t, and that's equal to tau. And the only thing you're doing is this term right there is just the time difference between these two, or if you subtract one from the other, the remainder is the argument that goes in there. All right, so if you look at this, and that is e to the minus magnitude of tau squared, well, I really care about that difference. So back over here, I hope you can see this. I know I'm pushing up in the corner, but can you see it back there?
Mm-hmm.
All right, for this one, what's the time difference? Well, you can take this one minus this one, or this one minus this one, but t plus tau minus t minus tau, yeah.
So you're really just trying to cancel out the t's? Here?
Well, I don't like that word cancel. You're subtracting the arguments, right? I mean, you'll never see 2t and then t here. This will never, if it's a legitimate correlation, will never be a function of time. It'll
Right.
only be a function of the time difference, which is tau. Can you see it, Alex? All right, well, what is the time difference between, I'm doing this one here, between this and this? It is just going to be tau minus tau 1, or tau 1 minus tau. Do you see it? I don't like the use of tau 1 because it kind of, the symbol tau is usually just given to the argument of the autocorrelation. But that means the difference is this. So I take the autocorrelation, I replace tau there with tau minus tau 1 squared. Can you all see it? You see it? What's the next one? You tell me. Just look for a second. I've got this one. What's the difference between either of these two arguments? Use this one first. T plus tau 1 plus tau minus t. Tau 1 plus tau, right? It's going to be e to the minus magnitude of tau 1 plus tau squared, sorry, plus, and what's the final one? Now, this is important, this part right here, because people mess this up. What is the difference between these two for that one?
It's just how, right?
Just tau. Can you all see that? And you'll notice this skew in time. Tau plus tau 1 appears in both, so forget about tau 1. It's just going to be a function of tau. So that one itself is going to be plus e to the minus magnitude of tau squared. And that should be what he has, yeah, right here. Now, I'm going to just give me 2 points right here and I'll move on. When you look at this, obviously you're going to get 2 of just the autocorrelation function of x, basically Rx of tau. Then you're going to get this first one, second one. Now, when you look at that, here's something real important. For all these functions, they have to have a peak when tau equals 0. If you look at this one, doesn't. Well, when tau is 0, what do you get? 2, right? Can you all see that? You get 2 here. What about this? You just get e to the minus tau 1 squared. Here, you're going to get e to the minus tau 2 squared, right? Do you agree with that? You see it's tau minus tau 1. Tau goes to 0, you get minus tau 1 squared, which is just tau 1 squared with a minus sign. You're going to get that. Now, maybe it's not apparent that clear right now, but you're about to hopefully see this. Because you do a lot of stuff that gets a little tricky shortly on this stuff. That's the reason I spent a little more time, even though it may seem obvious to once you see it, people will have trouble until they do. Okay. Next, now we do some homework, 6.1 and 6.2. And I'm doing it this way for a reason. I can get through this a little quicker. And I don't remember what these problems are, but I don't believe they're very difficult. You have the problems right there. Section 6.2 or 6.3 is the one that gets a little hairy. It actually gets much more difficult. Oh, for 6.1 and 6.2, for 6.1, let go. Give me that. 1 second. I'll go. This is 6-1.1, and what is it?
The stationary random process has sample functions of x of t and has an autocorrelation function of Rx of tau is equal to 5 e to the minus 5 absolute value of tau. Another random process has a sample function of y of t is equal to x of t.
Y of t equal x of t.
Plus beta x of t minus 0.1.
Okay.
Find the value of beta that minimizes the mean square value of y of t.
All right, so they want the value of b to minimize the mean squared value of this function y. Now, I think I mentioned this earlier, but the mean squared value of, say, x of t is just Rx when tau is 0. Because if you think of the definition of Rx of tau, that is the expected value of x of t times x of t plus tau, right? And Rx of 0 is just the expected value of x of t squared. If it's a wide sense stationary process, this is the mean squared value. Can everybody follow me on that? I just want to make sure I'm clear on this. So mean squared value is just of a function or of any kind of a random process is just simply the value of the autocorrelation at tau equals 0 by definition. Okay, now back to this. They want the mean squared for this, so we're going to calculate the autocorrelation first. You with me, class? And when you take a look, because what's the next part of this?
Find the value of the minimum mean square value of y of t.
Okay. But before we do, we're going to go ahead and we're going to get the autocorrelation y. That's the goal, first part. So to do that, that is going to be Ry of tau would be the expected value, see if you can do this, of x of t plus beta times x of t minus 0.1, that's the first part. And then you're going to multiply that by x of t plus tau plus beta of x of t minus 0.1 plus tau. And you're going to go ahead and, I'm going to see if I can talk my way through this. So Ry of tau. First, does everybody agree on that it's the expected value, that whole spiel of stuff, right? Agreed, everyone? Work with me on this, make sure you see it. I take the first, so I take x of t times x of t plus tau, and I want the expected value. Do you all agree that's just the autocorrelation function? When I take this times this, that's the autocorrelation function, I'll just put it in here. So that's equal to 5e to the minus 5 magnitude of tau. Now first, then I do the inside. This times this, right? I get the so I'm going to take it. It's going to be plus beta. Then I have x of t minus 0.1 times x of t plus tau. What's the difference?
Tau minus 0.1.
So take this, so it's going to be t plus tau minus this, all right? So it's going to be tau plus 0.1, isn't it, class?
Mm-hmm.
You all see that, right? All right, so it's going to be times 5, and it will be e to the minus, and it would be 5 magnitude of tau plus 0.1. Plus, that's the first, that's the inside. Now we get the outside. From here, can you all see this now? Just you'll get to it, this becomes second nature in a second. I take this times this. So I'm going to get a beta, right? And then when I do that, what's the difference? Use this argument because it'll leave tau positive. So it's going to be t minus 0.1 plus tau minus t is just going to be tau minus 0.1. Do you all agree with that?
Mm-hmm.
Take the difference between this argument and that argument. So it's going to be e to the minus 5 magnitude of tau minus 0.1 plus, and finally the last one. This times that. This times that. Well, it's beta squared. You all see that? Because you got beta, so that's going to, or b squared, whatever that is, plus b squared. And then the difference, use this one. So take this and subtract that from it. It's just tau, right? So it's going to be times 5 e to the minus 5 times the magnitude of tau. Now, first, you all agree with that? That would be the autocorrelation. You agree, class? All right, now, if I want the mean squared value, what did I say you do?
So we
Pardon
put
me?
X is 0.
Tau is
So
zero.
far as 0.
Tau is 0. You agree with that? With tau is 0, what do you get? Put it over here.
That's part A.
R y of 0 would be the mean squared value. What is it? So that'd be y squared. The mean squared value would be, just take a look. So I got 5 here, right? And then I got 5 beta squared here. So I'll just put it equals 5 times 1 plus beta squared. So it'll be that term, and that term. And then this term, what do we get here? So then I get plus, wait a second. There should be a 5 here.
Yeah, I was, yeah.
So it's going to be 5b plus 5b or 5 beta, and it's going to be e to the minus 5 times magnitude. And here, tau is 0, so it's going to be 0.1. And then, what's, yeah, it's 0. This is going to be times 2 then, because
Mhm.
both these can have the same order. So it's going to be times 2, or 10. And finally, the last one, no, I got the last one. So that should be it. These two terms for the mean squared value. And we could get a single number for that, by the way. Let me put it over here. So we get y bar squared, or y squared bar, pardon me, equal to 5 times 1 plus beta squared. Plus 10 beta, 10b, e to the minus 5 times 0.1, or really minus 1.5. And that should be the value. By the way, I put the answers up, I believe, didn't I, on this one? 6-1? Is that the right answer? It is?
Mhm.
Okay. Now, obviously, it's not numerical because we don't know the value of beta, but that would be it. What's the second part? Is that a small b or capital?
It's small.
It's capital now. Anyway, what's the next part?
Find the value of the minimum mean square value of y of t.
What, you need to find B first before you can do that?
For what?
B,
What do you need?
the value of B first.
Well, this is a general form. That would be the mean squared value for any b. All right, and you'll follow me? You give me any b, that's it, period. And
So then we need to differentiate to find the minimum of B, right?
and what he wants the minimum, or wait, say that again?
He wants the value of b that minimizes the mean square value of it.
All right, now you gotta take a derivative, set it equal to 0. And if you take a derivative of this and set it equal to 0, you're gonna get, let's see, so it's gonna be 10 times b plus 10 times e to the minus 0.5. And since you set it equal to 0, that looks like it's going to be negative, so I can get rid of the 10, and I get b equals minus 0. Equals e to the minus 0.5. Is that the answer? That would be the minimum. By the way, that minimum I didn't say this, but these are non-imaginary numbers. There's something that I think it's implicit all through the text that we're not dealing with any kind of imaginary numbers as solutions or even possibilities. The probability density function will not have any imaginary terms. Now, I've got to say this. In physics, has anybody had modern physics, quantum mechanics, anything like that? Have you heard of a thing called the Schrodinger equation? The Schrodinger equation is a very, very important equation, but it's a differential equation, second order differential equation, similar to the actual Helmholtz equation, similar to like del squared of, really, it would be second derivative e with respect to t squared plus, and then it's usually a del squared e equals 0. It's similar to that, second order spatial, second order temporal, but there are other terms. And the solution for the Schrodinger equation is a complex number, John. So psi, it's given by psi. And the probability density function, this is the important thing that comes out of the Schrodinger equation, is psi multiplied by psi conjugate, which means when you conjugate something, you flip the imaginary symbol basically. The angle, if it's positive, becomes negative. Now psi times psi conjugate is the probability density function. So if you can't, that's the hard part sometimes for people. If you take modern physics after you take this course in Rand, we've never talked about imaginary numbers because they're not observable in the real domain we live in. Imaginary numbers are something that allow us to solve things in the, you might say, in the frequency domain and in another domain, and then we can actually get the solution in the time domain that is observable by doing things. Remember when you have like 10 at an angle of 30 degrees, right? That's a complex number. Do you agree with that? To get it in the time domain, what you have to do, take 10 at an angle of 30 degrees times e to the j omega t, and you take the real part of that, and then you get 10 cosine of omega t plus 30 degrees, but it was the assumed relationship between the imaginary world, or I should say the phasor world, and what is in time. How do you get it to the time domain where it's observable? That's a long spiel on this, but I'm really telling you, if you get modern physics, that B right there can be imaginary. That's the ultimate thing. Anyway, getting back to this thing, what's the next one?
If the magnitude of B is less than or equal to 1, find the maximum mean square value of y of t.
Okay. Now that's a plot. If you're going to do that, if you actually plot this, mean squared value of y versus b, and he said, what's the range for b?
If the magnitude of B is less than or equal to
1? With no boundary, lower limit? All right, so what you need is a plot for this. And for this one, let's see here. So b's at a minimum at this value, right? This is going to be a quadratic. By the way, I think we might be able to get away with this. So this is going to be at minus 0, or I'm sorry, whatever this value is. What is e to the minus 0.5? I don't know what that is, but
minus 0.6.
is that right? All right, if you plot that, it's going to be a quadratic. And that'll be where the minimum is. Here's my argument. He says, find out where it's minimum between 0 and 1.
If it's less than or equal to
Find the
the
maximum.
maximum mean square value.
What?
The maximum mean square value. If it's less than 1.
Well, the maximum. That's a second order. That thing goes to infinity. There's not a lower, is it between 0 and 1? Or
B has to be, like the absolute value of B is less than 1.
oh. So that's from -1 to +1. Follow me? If the absolute value, that's from -1 to +1 is possible values for B. You all with me on this, class? Now if you look at that, if you plot B, this is a quadratic, and I'm sure this is the, matter of fact, I think I've read this, this is the argument he makes. If this thing, see, that's a beta squared and a beta, that's quadratic right there. You know it's gonna have this kind of behavior. So if the minimum's here, my argument is the distance from here to this point is greater than from here to this point. So right here at 1, it will be the maximum. That's the only, it's heuristic, that's the term they use. But you all see that? If you think about this, this is going to be a symmetric function right here. If that's a symmetric function, then my argument is the distance from here to -1 will render a point here that has got to be less than the distance from here to +1. So this will be greater. So is a value of 1 the answer to this? But that's not really, that's a plot. I'm not going to ask you a plot. I'm not going to ask you to do something. You could on your calculators, I think, do that fairly easily. Are your calculators capable of plotting and showing plots or not? Yeah. If they are, then you could do that. I mean, I could ask it, but I'm not going to. All right, that's the first part. It's just getting you exposed to this stuff. Next part, what did you ask? Next part?
That's it for 6.
Okay. We'll do 6 too. I was just going to fly through this and get into the next section, but the more I thought about it, the more I thought, Quiz Friday, you probably didn't look at anything. I better go ahead and go through this. And some of the stuff you're going to see at a little more detail in the communications class with Dr. Cognate. How many are taking communications here this fall? Okay, only 2. You haven't taken comm, have you? That's a good course, and it's nice to take that right after this, because it's fresh in your mind, a lot of this stuff. Okay, next, go ahead, next one, 6.
For each of the autocorrelation functions given below, state whether the process, state whether the process it represents might be wide-sense stationary or cannot be wide-sense stationary.
Okay, I'm just going to say one thing about this. Anything that isn't a function of just the difference in tau 1 or T1 and T2 is not going to be a legitimate autocorrelation. We'll do maybe 1, maybe 2, but this should not be in any way, shape, or form confusing to you. So, just give me the first one.
Autocorrelation of T1, T2 is equal to e to the T1 times e to the minus T2.
Equal what?
E to the T1 times e to the minus T2.
Oh, this is a tricky one. Y'all see that? Now, if you look at that, I can write that as e to the a, e to the b is just e to the minus, and you can have T2 minus T1, right? Or T1 minus T2 with a minus. Y'all with me, class? Okay. Now replace this with tau. E to the minus tau. Remember, there are a couple properties I didn't get at yet. Is the maximum for that at tau equals 0? No. You see how as tau becomes negative, it gets larger and larger and larger. Can everybody see this? So if you actually plotted that function versus tau, which is the difference in tau 2 minus tau 1, it would do this. So the maximum is not at 0, and it's also not an even function. So that is not legitimate. Is that the answer, by the way? Okay, that's the first one. Real quick, and I'll ask you guys to know this, but go ahead with the next one. You'll see this stuff.
Autocorrelation of T1, T2 is equal to cosine T1 times cosine T2 plus sine of T1 times sine of T2.
Cosine T1, cosine T2. Go ahead.
plus sine of T1, sine of T2.
These are trig identities now. For that one, sine A plus B, I think this is equal to the sine of T1 minus T2 over T1 minus T2. I believe that's right. That's called a sinc function.
I got cosine T1 minus T2, that one.
Over T, is that the cosine identity?
For the one you just wrote down, I got that one for part B.
Hold on. I haven't done these in a while. If I look at that, cosine A plus cosine B. I think you are right. I think you are right. My bad on that one. So this, I'm sorry about that. And it should, what this is, this should be cosine of tau 1 plus tau 2, correct?
Minus that two.
You're right. You are right on that one. My bad. I'm sorry about that. Yeah, there would have to, for the sine identity, you have to be dividing that by tau 1 minus the T1 minus T2 if you're going to get a sinc function. My bad on that. So that, in that case, this cosine's an even function. If you replaced this by tau, now that one, and you plot a cosine function that has a maximum of tau equals 0, but it'll have mini maximum. You all follow me on this? That's still legit as long as the maximum, the peak of all the peaks will be at 0. That's still legitimate. There's one thing about this, and if you take a look at that thing, for that cosine function, I believe that is a legitimate autocorrelation. Is that the answer? It is. It's a little, some of these things, these trig identities can be tricky. I'm not going to ask you trig identity kind of cool things on this, but it's important to at least be familiar with it. The next part, I remember these, part C is, what is that?
Autocorrelation is equal to e to the T1 squared.
E to the T1 squared?
Minus T2 squared.
Quantity T1 minus T2?
No, T1 squared minus T2.
Is this T1 minus T2 squared? Okay. E to the T1 squared. Now go ahead.
Minus T2 squared.
Minus just T2 or E to the T2?
They're all contained in the same exponent.
Oh, I see. So it's going to be E T1 squared minus T2 squared.
Yes.
Okay. This is something I could ask you. This is legit. So the whole idea is, what is that going to be? Well, that would be E, and here you'd have T1 minus T2 times T1 plus T2. You agree with that? And if you take a look at that for a second at least, you'll realize that it is not just the function of T1 minus T2 for starters. It also is it's a function of T1 plus T2, and we could keep playing around with it to find more problems with it, but it's not legitimate. As he say, it's invalid. And I don't even know the terms he uses. Does he give a reason for why it's invalid? Or I think I put this up there. I don't remember actually. I mean, some of these have multiple reasons why they fail, but this one I think.
It's because
not a difference in just T1 minus T2.
It's non-expressible as a function of T1 minus T2 alone.
Yeah, that'll work, but it's not symmetric. I mean, it's basically, it's going to have something where if you replace, you can't replace either of these by tau. I mean, you're going to have a function of some other value besides tau in there. All right. We can keep going. How many more are there? Like 5 in there?
No, it's just one.
One more?
Yeah, just one.
What is it?
Sine of T1 times cosine of T2.
That's the sinc function. Don't worry about that one. You can look at that later. Let's do, is that all the problems in that section, right?
Yes.
Okay. Now, I'm going to go to the next section, hopefully do some of the problems. I've got about 10 minutes. But I really want to do these. Those are not bad, but if you don't go through them, you're not going to see some stuff coming up. I think you can really mess up. So here, you know, we got 7. I guess we've had 7 people in this class a couple times. But this is a small number. It's coming up. This one I can go through fairly quickly. Section 3 is the tough one. And by the way, if you're reading ahead, Section 3 has an autocorrelation of a random process that's binary. They don't even try to prove why the autocorrelation is defined as such. But you're going to see that one is tricky. If you're going to spend time on this course, spend it there. Because that's the quiz is going to have this stuff on it coming up in Section 2. All right, properties, and we can go through this. I'll just tell you about this thing. For any of these autocorrelation functions, they'll always be symmetric, about tau equals 0. Always even functions. They'll always have at least, they'll have V peak at tau equals 0, but there could be multiple peaks of the same height. There has to be one at tau equals 0. Now, I want you to just follow me on this. The property area. Here they are. It's on a PowerPoint if you want to look. All right, the mean squared value we covered. Right there. It's a symmetric function. R of tau, Rx of tau is equal to Rx of minus tau. Has to be. Don't worry about the proof on that. Here's the one thing. Here's the way he says the value at 0 for tau equals 0 is equal to or greater than the value of Rx of tau at any other value of tau. Now this is an important one, and people will miss this on quizzes. You see this constant value? Anytime you have a DC component, say you got something e to the minus magnitude of tau plus 5. You with me on this, class? As tau goes to infinity, you get a value of just 5 squared. Can you all follow me on that? That would be, so this value out here, whatever it is really the mean value squared. This is real important to see. It will be. Don't worry about this plot as much as just listening to me. So we go down here. If it's periodic, in other words, if you have a sine or cosine by itself in an autocorrelation, there'll be a frequency dependency you'll be able to see. And let me show you this. When you have this, like x of t is a cosine of omega t plus theta, that's probably, of all the functions that you see the autocorrelation function of the real world in the real world that you see, the cosine sign is always there. You'll always see these things. And a sure way to find out if you got it or not with an autocorrelation. Once you look at this signal, this is the autocorrelation. Just take this, multiply it by itself, and add omega t plus tau, and then break it up into components. And you'll get a squared over 2 times cosine squared of omega t as the autocorrelation. And you can see that's going to have a frequency-dependent property. Can you all see that? Next. This is a biggie here. And you know, pardon. If you look at this for a second, this is important. If x of t is a 0 mean process, then assuming it's ergodic, we're not going to talk about non-ergodic, non-wide sense stationary functions. We're just not going to, not here. not in this course. So if you want, I mean, if it's got a zero mean, here's how you can tell if it has a zero mean. Let tau go to infinity, the function better go to zero. Remember I told you the DC component's gonna be whatever it levels. No DC component, it's zero, the mean is zero. This is a little further down the road, it'll be in, not in section 3, but in section 4. But you see how they have the function Rx and then the transform, the Fourier transform called spectral density, spectral energy density. We're going to be talking about this. There's a lot of reasons we do this. These things are much easier to get information from than the time-varying functions. Now here's some things that you can't have. And in the time domain, you can't have a flat top, anything with a flat continual top. You can't have any vertical sides, and you can't have any discontinuities in amplitude. Now the one exception is right there, the impulse function. That technically is an allowable autocorrelation. I'm going to tell you, the impulse function in the real world is a non-observable. You can't have something of infinitesimal time duration with an infinite value. I mean, but you can approximate it. So just remember that. You can approximate these things in the real world, but that's another story. All right, can that be an autocorrelation function square? No, it's flat. Flat top and vertical sides. Real quick. These aren't hard. Now, please take a look at this one. If you just saw that, and I asked you what the mean squared value was, what would it be? Just take a look. I know the answer's in front of you. Well, you let tau go to 0, so you get 25 plus 16 plus 36. Follow me? Just by observation. There's nothing you do but add up the numbers. What's the mean value? Well, here, this is a tricky one. What is? Take a look at this one. Tau goes to infinity. You see how this one goes to 0, right? First part. This one oscillates. Can you see that? But what's the mean value of a cosine function? Ask yourself. Technically, when tau goes to infinity, that's undefined, but it is 0 for the cosine. And any kind of fluctuating component's constant, either sines or cosines. Here, without you don't even worry about that. Just get rid of it. Here's the mean squared value. I'm sorry. Here's the mean value squared, and that's 36 is equal to the mean value squared. So it's plus or minus 6, but you can never tell the sign from the autocorrelation. Only can tell the magnitude. Now, the variance, and the variance is kind of obvious. If you've got the mean squared value and the mean value, you square the mean value, and you can get the variance of 41. This is just to show you what can be asked and how simple it is. If you ask this, though, and I've learned this lesson, if I ask it before going over it, people will fumble. They do. And it's not that it's hard, but people aren't sure. All right. Now, this one, I gotta tell you, these numbers are a little tricky. If you look at that one, what's the mean squared value? How do you determine that? Let one.
Tau equals 0.
Pardon me?
Tau equals 0.
And what is it? 36 over 4, right? It should be 9. Yeah, it is. How do you get the RMS, or the mean value squared? Let tau go to
Infinity.
If it goes to infinity, what happens? Well, can you see the 25 and 6.25, this tau squared and this tau squared are going to infinity the same rate?
Mm-hmm.
You can divide top and bottom by tau squared if you want, let tau squared go to infinity, but you're going to get 25 over 6.25, and that's 4. It's an odd thing that he chose 6.25, but I didn't write this, he did. And it is 4. And finally, the variance. And by the way, variance can never be negative. Just remember that, because people will reverse these things and get a negative value. It can't be negative. It's that simple. Now this one's a little tricky. And this is something that I really want to make sure I drive this point home. Just give me a second. So they give you this. And so what value of A would make it a valid autocorrelation? Now just think about this. Is it symmetric about 0? Well, it is, because you see that's a magnitude of tau there. Now, the thing is, the maximum has to be at 0. So the only way you're going to find the maximum is take a derivative of of this thing and set it equal to 0. And by the way, I didn't say this, but back with the Fourier transforms, the Fourier transform of any legitimate autocorrelation is strict positive. It has no negative parts to it. And if you remember, we'll have to do some of these things. You remember, like if you have a pulse function or a rect function, in the time or in the frequency domain, it's a sinc function where it has positive and negative values. So a rect function can't be a legitimate autocorrelation. All right? But if you think of, do you remember a triangle function? Looks like this in the time domain. It has a sinc squared. It's tau over 2 sinc squared, or I'm sorry, yeah, tau over 2 sinc squared of omega tau over 4. That's legitimate because a sinc squared is magnitude positive. So anyway, we're not going to do the Fourier transform, but we're going to do a derivative. And yeah, take the derivative and set it equal to 0. Well, he's going to get an inequality. And at the end of the day, he says for 6, or for a less than or equal to 6. And in fact, you can look at that. I know I'm a minute or two over, but finally he does a Fourier transform of it. I want to say this. Does everybody know how to do a Fourier transform of like e to the minus magnitude of t, at?
Not off the top of my head.
That's a two-sided. It's basically going to be something where if you do that, it's going to have a 1 over omega squared plus a squared term. And you'll have to just trust me on that one. There'll be an omega on top too. But anyway, for this one, Fourier transform of this, or it's going to have sort of just omega squared. Down here, when you do the Fourier transform, you get this because it is something that exists for negative values and positive values. It's just not e to the at or minus at. And when you do this, you get this mess, and there is an omega squared here. And what he did is get a common denominator. Anyway, so if you look at this, this is the value for a that would make this legit, or strict positive, and it's still a less than or equal to 6 is the dominant one. All right, now for this one, this is where I stop. Just look at this. Is that 10 e to the minus 4 magnitude of t minus a? Is that symmetric about 0?
No?
It isn't, unless a equals 0. Y'all see this, class? And at a equals 0, it's a trivial function. It's just e to the minus 4 magnitude of tau. I'm going to leave that one. I'll give you some problems in this section so you can mess with it. But the PowerPoint's really good for this section. And I'd like you to, if possible, take a look at section 3 also. And on Wednesday, I'll discuss this stuff in a little more detail. All right. I didn't go over the quiz, frankly, because a lot of people weren't here. I thought they might start showing up later. But if you have any questions about it, just let me know. But it was meant to be, that's the homework problem. We did with slightly different numbers.